Harry, with that, I'm going to turn it over to you.
Well, great. Thanks, Mike. As Mike said, my name is Harry Woebkenberg. I am product manager for Jordan Valve, and this morning we're going to talk about the basics of pressure and temperature regulators, industrial pressure and temperature regulators. I am, and this is brought to you, of course, by the Lesman Instrument Company. I am joined here in Cincinnati by Tim Gaynor, who's a regional manager for Richards Industries. Like I say, we're going to talk about industrial regulators. We'll talk about pressure reducing valves, back pressure regulating valves, temperature regulators, and tank blanketing regulators. Again, as time permits, we'll cover as much of these as we possibly can. We'll have, of course, you can type in questions, but we'll also have time for questions at the end of the presentation. So if you have anything that you want to bring up at the end of the presentation, we can do that as well. And let's start out on our journey to explore regulators here. The regulators are simple self-operated control devices which operate off the process itself. Okay, a control loop. Wonder why a control loop, but I put a control loop up there because most people are familiar with control valves and control loops. It's one of the things that they teach in school, but they don't necessarily teach people about regulators. But regulators, you'll find, do a lot of the same things that control loops do. The three major elements of a control loop are the sensing element, which measures the process variable being controlled, and that then sends an output to the controlling instrument. And the controlling instrument, or the controller, calculates the error, which is the difference in signal from the sensing element and the desired set point, and sends a corrective signal to the final control element. And then in a control loop, the final control element, which is the control valve, varies the flow to change the controlled variable to the required set point. So basically, a control valve is kind of a dumb device, and it needs something to tell it what to do. So we're going to see that regulators have a lot in common with control loops. Here's a quote from a gentleman named Hans Baumann, and he says, properly utilized, regulators could replace control valves in at least 25% of all control loops. The reason that this is a significant statement, for those of you who know who Hans Baumann is, you probably already know, but he's an inventor and engineer. He has over 200 patents. He's a PhD in mechanical engineering. He's been published in the Instrument Engineer's Handbook, Control Valve Handbook, Noise and Vibration Control Engineering Handbook, and he also developed the Mason-Elan Camflex valve, the Cashco Ranger, and the Baumann Little Scotty valve. So here is a dyed-in-the-wool control valve guy, obviously one of the biggest influences in the development of control valves, of the past generation, and he's saying that regulators could replace control valves in at least 25% of all control loops. Strong statement from a control valve guy. What does that mean to you? Regulators can be a great savings, again, in the proper application. Now, here you see a cutaway picture of a regulator, fairly simple device. You have a spring in the spring housing. You have the body of the valve where you have a diaphragm that rests between the spring housing and the valve body, and then you have a valve plug. This is a cutaway of a pressure reducing valve, or what we call a PRV, and we want to control the downstream pressure, or the P2. And basically, when we talked about those similarities between a control loop and a regulator, you can see here that the spring acts as the controller, the diaphragm acts as the sensor, and the plug and stem mechanism make up the feedback mechanism. So as the downstream pressure is sensed, it acts on the diaphragm, or the sensor, the pressure sensor in this case. As it overcomes the spring, it will drive the spring up, and in this case, closing the valve, because you want to cut the pressure off once you reach the desired set point. As the pressure falls, again, the spring will overcome the diaphragm and moving the valve back to the open position. So it basically does the same thing as a control loop, only in a much smaller package. Now we're gonna give some things away to be able to take advantage of the simplicity, and we're going to talk about that as we move through the presentation today. But so a regulator, the basic characteristic, you can consider it a standalone, self-actuating controller. What should you expect from a regulator? All of the things we're going to talk about here are somewhat relative. So we're going to talk about accurate regulation. Is it as accurate as a control valve? No. However, you can have accuracies in regulators anywhere from 70% accurate to about 98% accurate, depending upon the regulator that you choose. Tight shutoff. Again, if you have a metal-seated valve, typically you're going to achieve ANSI Class 4 with a hard seat, and you can achieve ANSI Class 6 shutoff if you have a soft seat. Fast response. Faster response than a control loop, because all the external communication doesn't have to take place when you're using a regulator. Minimum maintenance. As you saw in the picture, in the picture, the cutaway that we looked at just a minute ago, there are not a lot of parts. It's a fairly simple design. Some manufacturers actually have smaller valves, 2-inch and under, that have no soft parts. There are no O-rings. There are no gaskets. Really no soft parts to wear out at all. So minimum maintenance is simple, if needed at all. By design, they're low noise, and it's a low initial cost.
And one important part on the maintenance element, if you have a control loop controlling pressure and it's not working correctly, you have a lot of different components to check. Is it the sensor? Is it the valve? Is it the programming of a PLC or DCS? There's a lot of different things that you have to check, whereas if you're using a mechanical device and you're having an issue, then troubleshooting is going to be a lot simpler.
Advantages of using a regulator. No external power is needed to position the valve. So you do not need air, you do not need electric, you don't even need an operator to go out and stroke the valve. No need for separate measuring elements or feedback controllers. Once you go out and put the regulator in line and set it to your conditions, it is going to do what you set it up to do for a long, long time. Again, the designs tend to be simple, providing low cost, high reliability, and easy maintainability. The absence of stem packing eliminates external leakage and a high source of friction. And regulators are in direct contact with a controlled variable and offer very fast response. As we saw in the cutaway, as the pressure acts underneath the diaphragm, it'll compress the spring, and depending upon whether it's a pressure reducing valve or a back pressure regulating valve, it will then move the sealing member to the appropriate position. Regulator limitations. The controlled media must be relatively clean and benign as materials of construction are limited. This has changed somewhat over the last several years. There are some manufacturers now that actually manufacture regulators in exotic materials. So the benign piece of this tends to not be as big an issue as it was in the past. However, the relatively clean is still important. Most manufacturers will actually recommend putting a strainer in front of a regulator as part of the preferred installation. Regulators lose controllability when the pressure drop across the valve becomes small because the media cannot supply enough operating power. If you have an extremely low delta P in a valve, sometimes that can be a problem. Many valves will actually state a minimum delta P requirement. Operating points are not constant due to droop. That's a term that may be new to some of you that are on the call today, but we'll cover that in the next few slides and talk about droop and how it relates to the accuracy of the regulator. But there will be some inaccuracies in the control just due to the design of regulators in general. Regulators cannot accommodate anti-noise or anti-cavitation trims, and failure modes are fixed. So those are some of the limitations that you run up against and you need to consider when specifying a regulator for an application. Okay, do not use a regulator when, this one seems like a bit of a no-brainer, but when the desired pressure or temperature set point is beyond the range of a regulator. Again, this can be due to design. This can be due to materials of construction. Sometimes because of pressure and temperature considerations, you may have to move out of a regulator and into a control valve. Don't use a regulator when process offset cannot be tolerated. If you need to be accurate within 1 to 2% or less, you're going to have to go to a control valve. Don't use when the pressure drop is extremely small or extremely great. Don't use when a fail-safe feature is required. So if you need one to fail open or fail closed or fail last, you can't necessarily do that with a regulator. Sometimes because of the way the valve is built, that might work out for you, but again, if you just have to pick one, it might not always be doable if you need a specific fail position. If the system requires control of a multivariable process or if feedback is required. So those are times when you want to avoid using a regulator. Okay, here's that word droop again, or inaccuracy in regulators. It's also known, or you might hear it referred to as proportional band or offset, but it's the deviation from the set point as flow increases through the regulator. And this is normally expressed as a percentage. So if you have a set point of 100 psi, and when you get to full flow through the regulator, your pressure is 80, then you would have droop of 20% or 80% accuracy in the regulator. So the pressure falls below the set point in the pressure regulating valve. In a back pressure regulating valve, it's called build or gain. And generally, the lower the droop, the better the regulator. And manufacturers typically specify ranges from 2% to 30%. Now, an important thing to when you look at that, you think, oh, that's a massive range. And in fact it is, but you'll see where 3 different types of regulators each own a chunk of that 2% to 30% range. You have one type that's going to be 2 to 5%, one that's 5 to 10, and the last self-operated or direct-acting regulators are going to take up the rest of that 10% to 30% range. So there is a hierarchy that we're going to discuss in regulators, and all 3 types are going to make up that 2% to 30%.
And one question you may want to ask yourself is, why do I care about this? What you want to consider if you were utilizing a regulator on a steam system, for example, and perhaps the distribution goes to a number of vessels or cookers or heat exchangers and the loads vary. Well, all we want to do is help you look at the options that are out there so that you can ensure a constant supply of steam. If the demand changes a lot and you have droop, then your 80 psi steam may fall down to 60 and you don't have as a reliable supply or the pressures that you need to accomplish what you want to do. So we want to minimize that droop so that you have a good supply of steam to your user points.
Okay, there are 3 variables that determine droop in pressure regulators. Stroke length, the shorter the better. So, the shorter the stroke, the more accuracy you're going to have in a regulator. The diaphragm area, the larger, the more accurate. You see tank blanketing regulators with massive diaphragms. And those are ones where you don't want to see much droop and you need incredibly accurate regulation. But that's not, manufacturers, that's not reasonable for them to put those massive diaphragms on every regulator that they manufacture. Additionally, oftentimes in your applications, you're not going to have the room to accommodate some of those massive diaphragm areas. And the diaphragm material has an impact here as well. And then spring rate, the lighter the spring, the more sensitive the regulator. So you want to have a spring or specify a spring rate in your regulator that includes, of course, your set point, but is as close to that set point as you can possibly have, because that's going to give you much more accurate regulation. This is a typical droop curve. You can see, if I can get my pointer to work, hopefully everybody can see that. But here's your set point. Let's say, for instance, this is 100 psi. And the regulator will droop off, and let's say when you get here moving towards full flow, you get to 80 psi. So again, expressed as a percentage, you'd have 20% droop based on this particular curve. Regulator sizing. A lot of problems, and one of the things that will help in the accuracy of regulation is correctly sizing the regulator. And at a minimum, the information needed is the required flow capacity of the valve. Usually, users will always have normal, but it always helps if you have minimum, normal, and maximum. And if you have a minimum of 1,000 pounds an hour, but you have maximum of 20,000 pounds an hour, that means you're going to have to be able to accommodate a 20-to-1 turn down. So that's important information to know. Inlet pressure to the valve, obviously the outlet pressure or P2. So in a pressure reducing valve, that's going to determine the set point. So what, again, your inlet pressure could be 150 psi. You want to reduce it to 80 psi to use at other places in the plant. So that's why that's important to know. And also the service, the media, viscosity, and specific gravity. So generally, the more the manufacturer knows, the more they're going to be able to help you choose the right regulator for your application. Generally, you can use an ISA control valve data sheet. A lot of the same material or a lot of the same information is going to apply. And again, at a minimum, the requirements are inlet pressure, outlet pressure, flow rate, and the medium. And again, the more manufacturers know about what your process conditions and what you're trying to do with the valve, the better fit you're going to get, and obviously the best service life you can possibly get. So if you have that minimum, normal, and maximum condition, temperature, service, viscosity, specific gravity, on and on. The more, again, the more information that a manufacturer has, the better they're going to be able to work with you and put you into the right product. Here's the regulator accuracy hierarchy that I mentioned earlier. We have self-acting or direct-acting regulators. These are what people generally just call set and forget. And manufacturers, depending upon their designs, will normally claim 10% to 30% droop, or accuracy of 70 to 90%. Piloted regulators, this is where we have a small pilot valve that's going to run a bigger valve. So you have enlarged diaphragm surface areas on the big valve, and your droop comes down to 5 to 10%. So very much more accurate than a self-acting or direct-acting regulator. And then finally, you have air-loaded regulators, where the spring is eliminated. So one of the three variables that go into the droop equation goes away. So droop here is generally in the 2% to 5% range. Sometimes you can even improve on that a little bit. But basically, what you're talking about here is regulation that's going to rival a control loop. It allows the use of extended range I to Ps. You can control via 4 to 20 signal, and again, faster response than a control loop. How do you choose? This is a very simple little matrix that if you look on top at self-operated regulators, droop, again, 10 to 30%, and rangeability, 10 to 1. So if basically you're talking about the highest controllable flow to the lowest controllable flow, or reasonably well controlled, and so 10 to 1. So you could go 100 down to 10, or you could go to 1,000 down to 100, or somewhere in there. Pilot operated regulators, on the other hand, less droop and higher rangeability. So when you're looking at self-operated, faster and lower cost initially. Pilot-operated regulators, higher accuracy, greater capacity. So those are a couple of things that you want to consider when you're thinking about choosing a regulator. Okay, pressure regulators, or pressure-reducing valves, normally called PRVs, and these are self-operated devices which work off the medium alone. And again, well, you'll hear pressure-reducing valves referred to as PRVs, and what this does, it lowers the inlet pressure to the desired set point. So we're talking here about controlling pressure only. Here's a cutaway of a pressure-reducing valve, and again, you see the spring, the diaphragm, And here the sealing member is a little different than the one we looked at earlier, but you have your flow, which is P1. Okay, let's say it's coming in here at 150 psi. You want to take it down to 100 psi, or P2, your controlled pressure, downstream pressure here, you want to have it 100 psi. So you put it in, you set it to your conditions, and it's regulating to 100 psi. How does it do that? In a self-operated valves, especially in smaller diameter valves, they're going to have an internal pressure register, so that it's going to sense the downstream pressure up along the stem and up under the diaphragm. Okay, when this is in the normally open position, the springs keep it that way. So when you hit that set point, that pressure set point, and start to exceed it, what's going to happen, the pressure is going to act on the underside of the diaphragm, compress the springs, and take the seats to the closed position. Okay, as it senses that the pressure is falling below that set point, again, the springs will overcome the line pressure and will push the valve back towards the open position. And that's how this will modulate and regulate the downstream pressure. Here's a typical pressure-reducing valve application. The customer needs to reduce the pressure on a steam line. The pressure off the boiler is 175 psi. Pressure-reducing valve, he wants to reduce it to 100 so he can use it other places in the plant. So a very simple, very basic application, but there are an awful lot of those out there in the field. And this is ideal for a self-operated pressure-reducing valve. Now we're going to start moving into that hierarchy of accuracy that we referred to earlier, and we're going to talk about piloted regulators. With a pilot regulator, the set point is determined by a pilot, which is a direct acting regulator, that controls the flow to or from the diaphragm of the larger valve. Most piloted regulators do have a minimum differential pressure requirement. That will vary based on manufacturer, but normally they're in the range of 10 to 15 psi minimum delta P. Here's a picture of a piloted pressure regulator. As you can see here, this is the pilot valve, the one with the red dome. And the pilot valve is going to drive the larger valve. So what this does, you can have a very small pilot, half-inch valve that can drive valves generally up to 6-inch, so you can have larger line sizes and higher flows. Extremely accurate. These are accurate now to within 5 to 10% of the set point, which, again, much more accurate than a self-operated valve. Higher turn-down ratios, as high as 35 to 50 to 1. But again, it does require a minimum differential pressure and a downstream sensing tap. On the self-operated regulator that we looked at earlier, that was an internally sensed or an internal register. This is going to have an external register, and underneath the diaphragm, you'll have a sensing line that's going to go sense the downstream pressure. Okay, and so that's going to send a signal up underneath the diaphragm to let you know, and you're going to control it to that pressure. You're going to respond to the pressure that's in the line. And the advantages of piloted regulators: more accurate. They begin to rival a control system. Less droop, again, 5 to 10% range. They're more sensitive. So a small change in the pilot is going to mean a large change in the main valve. This can also be a disadvantage, and we'll explore that in just a minute. And again, the higher rangeability, as high as 35 to 50 to 1. Disadvantages of piloted regulators: they're more sensitive. That can create oscillations within a system, and we talked about how it can be an advantage. They're not good in rapidly changing systems. Again, you can begin to overshoot pretty dramatically if your load changes rapidly. So these are for systems that don't have rapid changes in the load, and they do require a minimum pressure drop to operate. Again, about 1 bar. Dome-loaded pressure regulating valves. Here you can see the flat dome. Okay, everything else we've seen, we haven't seen anything like this. But what we do is we eliminate the spring, and by doing that, we take one of the variables out of the Droop equation. So these tend to be extremely accurate, generally in the 2% to 5% range. You'll put an air signal across the top of the diaphragm, and that is how you determine your set point. So you need an air regulator or an I to P, but still this is much faster than a control loop. You have increased rangeability, low, if any, minimum delta P requirement, and these are excellent for frequently changing set points or remote installations. If you have a set point that might change several times a day or several times a week, you can take an air set or a point of use regulator and change the load on top, therefore changing your set point. Or if you have this 20 feet in the air, instead of having an operator have to take all the safety precautions and go up there and change the set point, this can be done remotely with a point of use regulator. So very handy in that regard. Typical regulator applications. Again, you have to use it in systems requiring control within 2% to 30%. And there are a myriad of set and forget functions. Pump bypass, steam heating, pressure control, gas cylinder pressure control, tank blanketing, back pressure. You see regulators more than anywhere else in utility applications. So you're looking here, regulators tend to be excellent in steam, air and other industrial gases, both hot and cold water, lube oil, and any other utility application that you might be able to think of. Typically, regulators work particularly well there, and they're cost effective in those applications as well. Now looking at back pressure regulating valves. These are designed to modulate and hold a specific back pressure. They're not a relief valve. They actually are modulating, regulating valves. They monitor and regulate upstream pressure here. When we were looking at pressure reducing valves, we were actually controlling the downstream pressure, or the P2. With a back pressure regulator, we're going to regulate P1, or the upstream pressure. They're also known as reversed acting regulators, and Droop here is called build. So when you have a deviation from set point in a back pressure regulator, the pressure tends to build instead of droop. Here's a typical back pressure application. You have a pump running, you have downstream demand. In this particular instance, let's say we only run 1 or 2 shifts. So at 5 o'clock, demand shuts down, but they want to keep the pump running. In order to avoid any kind of damage to the pump, as pressure starts to build back from where you've shut down the demand, all of a sudden pressure is building. You have a sensing device as part of your back pressure regulator, and once you meet or exceed your desired set point, this valve is in the closed position, but once you hit the set point, it will open relieve the back pressure and control the back pressure so you can continue to run your pump. Probably 85 to 90% of all back pressure regulator applications are on pump bypass of some type or another. Another type of regulator that you may see is called a tank blanketing regulator. These are used for gas blanketing or other low pressure air and gas application. Extremely large elastomer diaphragms in these particular valves and very light springs. The reason for that is they have set points as low as 1 inch of water column. And tank blanketing, or padding as it's often called, is the process of applying and maintaining a constant gas pressure in the empty space of a storage tank. So if you have, for instance, a volatile or toxic commodity, tank blanketing can prevent harm to workers, equipment, the environment. If you have a commodity that's perishable, like a food or other substance, tank blanketing protects it from oxidation or contamination through exposure to air or moisture. So that's why people use tank blanketing regulators. Normally, the blanketing media is nitrogen. Due to its inert properties, it's readily available, and the cost is relatively low. So again, you have blanketing regulators. Here again, we have self-operated regulators. The one in the cutaway in the picture here is actually an internally sensed regulator, but you also have piloted blanketing regulators, and a lot of them will actually have an external sensing line, again, that's attached to where you want to regulate the pressure, which would be inside the tank, and it reads that pressure underneath the diaphragm, and that's what drives the valve. Temperature regulators. Now, this is a little bit different, and again, we're talking about industrial regulators here. So these are very robust, self-operated devices in which the energy to position the valve closure member is provided by changes in temperature energy of the control variable. No air, no electric, no operator required to make these valves work. They're totally mechanical. There are self-operated valves, and there are piloted temperature regulators available in the marketplace. This is a picture of a self-operated temperature regulator, and these are used for a myriad of applications: tank heating, heat exchangers, steam tracing, et cetera, et cetera. They can handle set points from -40 to +450. Very accurate, plus or minus 2%, and they'll run the range full closed to full open, or vice versa, in as little as 10 degrees F. Basically, what you have, this is a sensing bulb, and it's filled with a thermal fill that will have a specific boiling point. As this will be placed in a thermal well, or in some cases they'll hang it in a tank. They'll hang it in the ambient air, depending upon what they're trying to do with the valve. But there will be a thermal fill that will be within the end user's specification in terms of what they need to control temperature-wise. As this hits the boiling point, the vapor fill will boil off and drive an actuator, and the actuator will drive the valve to the desired position. And again, very accurate, totally mechanical. So it's a great option dependent upon the application. Ambient temperature regulators. Here, this is just sensing ambient air, so you no longer have the capillary and the sensing bulb, and this is for steam tracing to protect freezing of outside instrumentation, pipelines, and tanks. Again, no air or electric is required, and this handles ambient temperatures from -5 up to 210 F in terms of what the set point can be. And finally, there are externally piloted offerings available in the marketplace. For critical temperature control applications, it's going to be more sensitive. And in this case, the picture here is showing a temperature regulating valve acting as the pilot for the larger valve. So higher flows, you can have these as large as 6 inch in diameter, wider rangeability, just like piloted pressure regulating valves that we looked at before, and greater accuracy, again, because it's piloted. So in summary, pressure and temperature regulators, when sized correctly and properly applied, will provide accurate regulation, dependable performance, fast response, low noise, and minimum maintenance. What to choose? Obviously, there are many applications for both regulators and control valves. The big question, and the question that you need to ask yourself, is, for my money, how much accuracy do I need? And that is Regulators 101. I want to thank everybody for their attention today, and thank Lesman Instrument Company for sponsoring the event. Thanks again.